Okay, now we have arsenic acid reacting with lead-4 hydroxide. This is forming lead-4 arsenate and water. We begin by asking, we have an acid with 3 hydrogen ions, a base with 4 hydroxide ions. What's our least common multiple? Well, of course, that's 12. So for 12 hydrogen ions, we need 4 arsenic acids. For 12 hydroxide ions, we need 3 lead-4 hydroxides. When it comes to the salt, there's always just one of them. And that salt must have how many leads? Well, there's 3 on the left. How many arsenates? There's 4 on the left. And 12 hydrogen ions got together with 12 hydroxide ions to form 12 waters. I hope this is what you came up with. Okay, onto the strengths of acids and bases, and I would remind you that strong acids and strong bases were examples of strong electrolytes, so they form high concentrations of those hydrogen ions. And weak acids and weak bases form low concentrations of ions, so low concentrations of those hydrogen ions and hydroxide ions. So again, strong acids and strong bases do a great degree of ionizing, forming high concentrations of their ions. Weak acids and weak bases are going to form limited amounts of their ions. Now when it comes to the meta-ionic equations, they're going to look a little bit different. Because in a solution of strong acids, we have separate hydrogen ions and the anions. In solutions of weak acids, well, we would expect them to stay in their original formula. Same concept for strong bases versus weak bases. Strong bases are going to exist as their separate ions, and weak bases as their unseparated formula. Okay, so when we have a strong acid with a strong base, we have the hydrogen ion and the hydroxide ion forming water. The counter ions would be spectator ions. But just do note, strong acid, we have hydrogen ion and the anion, strong base, hydroxide ion and the cation, and then those ions remain unchanged. In a strong acid with a weak base, well, the base actually does stay the same, so it didn't separate into ions. So for example, let's say that the base is ammonia, or a limited solubility hydroxide like aluminum hydroxide. Well, then when we add a strong acid to it, the hydrogen ion, it picks up that hydrogen ion to essentially either form like ammonium, NH4+, or we might neutralize one of those hydroxides. A weak acid is going to exist as its unionized form, so that's HA, that's a little bit easier to illustrate. And then strong base is going to exist as hydroxide ion and its counter ion. And again, the counter ions don't show up because they would still be in solution. But we would see the result of the base reacting with the acid to form the anion of that acid. Okay, onto acid-base stoichiometry and reverse stoichiometry, how one chemical relates to another when it comes to acids and bases. Well, pretty much like any other balanced equation, they relate through their coefficients. So let me illustrate this with an example. We're asked how many moles of phosphoric acid are needed to neutralize 125 milliliters of a 0.255 molar sodium hydroxide solution. Okay, we're given information on phosphoric acid and asked about sodium hydroxide. We know we're going to have to go through moles and we need that balanced equation. So that would be a good preliminary step. Let's write out the unbalanced neutralization reaction where phosphoric acid is reacting with sodium hydroxide. It's going to form the salt of the sodium and the phosphate and water. Don't be fooled by me writing the water and the salt in opposite order. Okay, and then if we do have a salt already written out for us like we have here, we can actually work backwards. So I see 1 phosphate on the right. How about I put 1 phosphate on the left? And then 3 sodiums on the right. let's put 3 sodiums on the left. And then 3 hydrogens from the acid, 3 hydroxides from the base forms 3 waters. It's just an alternative way if you already have the formula of the salt. And that also shows if we forget how to balance a neutralization reaction from the balancing standpoint, just come up with the formula of the salt and work backwards from there. We already know how to come up with the formulas of ionic compounds. Okay, we're ready for the calculation. Oh, actually, we do have one more preliminary step, don't we? Pulling out that conversion factor, that concentration term. All right, now I think we're ready for the calculation. So step 1, how many moles of phosphoric acid? Step 2, well, now we know we're looking for a number with a single unit to start the calculation with. And only one number with a single unit, 125 milliliters of solution. And now step 3, out of milliliters, can we go straight to moles of phosphoric acid? Remember, this is milliliters of sodium hydroxide. Can I go straight to moles of phosphoric acid? No, I'm going to get 2 moles of phosphoric acid from moles of sodium hydroxide. So first into liters of solution, and then from liters into moles. We've seen this in several of our solution stoichiometry problems previously. And now, out of moles of sodium hydroxide, can I go to moles of phosphoric acid? Since we have them both in the same balanced equation, the answer is yes. And for the numbers, 1 milliliter, 10 to the negative 3rd liter, 0.255 moles of sodium hydroxide for each liter of solution, and 3 moles of sodium hydroxide for each mole of phosphoric acid. Or 0.0106 moles of phosphoric acid. Now note, if we were given the volume of the solution that we just neutralized, we could put the number of moles over volume and give the concentration of that acid in moles per liter. Okay, actually let's look at this problem. Note the 0.255 molar sodium hydroxide, 125 milliliters. Actually, I'm just going to change that to 0.125 liters. And then there's our balanced equation again. Okay, now we're after the concentration, so we're after moles of phosphoric acid per liter of phosphoric acid. And I would fully label these because we have information on the sodium hydroxide as well. We don't want to confuse the two, so fully label them. Step 2, if we're finishing with 1 unit per another, then we're starting with 1 unit per another. And now I have 150 milliliters of phosphoric acid solution and 0.125 liters of the sodium hydroxide. We've already identified that 0.255 big in bars, not a single unit. So between the milliliters of phosphoric acid and the liters of sodium hydroxide, which is going to go on the top? And it's actually the liters of sodium hydroxide. As we saw a while ago, the volume of sodium hydroxide took us to moles of sodium hydroxide, which took us to moles of phosphoric acid. We can also see what's going to give us liters of phosphoric acid, and that would be the milliliters of phosphoric acid. So I hope that one of these two ways helped you put the correct units in the correct order. Okay, on to step 3, out of liters of sodium hydroxide. Can we go straight from liters of sodium hydroxide to moles of phosphoric acid? No, but I can go to moles of sodium hydroxide using that concentration term. And then from moles of sodium hydroxide, we can go to moles of phosphoric acid. This is very much what we did in the previous problem. What's new is now we have the volume of the phosphoric acid, and let's get out of that milliliters, which is on the bottom, so we put it on the top. And ask, can we go from milliliters to liters? And yes, we can. And our setup is complete. That was 0.255 moles of sodium hydroxide per liter, and that's 1 mole of phosphoric acid per 3 moles of sodium hydroxide. We get that from the balanced equation. And 1 milliliter, 10 to the negative 3rd liters. Like put this on my calculator. I come up with 0.0707 moles per liter. Does our answer seem to make sense? It does seem within the range of reasonability. Note, if I put that 10 to the negative 3 with the milliliters instead of the liters, I would get 0.0000707, and that would definitely seem a bit small. Often the size of your answer will tell you if you've made a mistake. Okay, the analytic technique where we get the information, how many milliliters of sodium hydroxide neutralize so many milliliters of that phosphoric acid, is called a titration. So again, this is an analytic technique that's done in the laboratory. It's done using a burette, and that's what we see here on the left. And it's a tall tube which has gradations for the volume, and it usually starts at 0 at the top and then goes down, and most are about 50 milliliters. Now, why does it start at 0 and go down? Because if you start with your burette filled up to the 0 mark, and then as you add the titrant, the liquid inside, and it finishes the titration, finishes the reaction at, say, 26.5 milliliters, well, then we can see right there that would be the volume of the titrant that you delivered. Now, if you don't start on 0, that's okay too. You'll just have to subtract whatever you started with. So let's say you started with 1.2. Well, then you would subtract that 1.2. So again, this is the analytic technique where we fill our burette with our known solution. So that would have been the sodium hydroxide of the known concentration from the last problem. And then we would titrate, we would react this with the unknown, that would be the phosphoric acid. And then we'll have some way to tell when the reaction is done, like maybe a pH measurement, or maybe we have a color change. That's an often case. We'll see a color change, and we'll see that in the lab here. Okay, let's practice some of the things that we've learned using the following net ionic equation. We're asked what volume of a solution of 0.110 molar cobalt-3 nitrate is required to form 1 gram of solid cobalt-3 hydroxide. Okay, it's not a limiting reactant problem, but I am going to set it up where I'm using my units, and I do have a preliminary step, don't I? So I've identified I'm using my units, and I've identified my preliminary step of extending that bar and writing moles over liters. Then, using my units means step 1, we're after the volume. I'm going to go with milliliters. Step 2, well, only that 1 gram is a number with a single unit attached to it. Here comes step 3. Let's get out of that starting unit. Once again, getting this bar should be pretty easy. Now comes the big question. Can I go from grams of cobalt-3 hydroxide to milliliters of cobalt-3 nitrate solution? No, I'm going from one chemical to another, so we know we have to go first into moles. So into moles of cobalt-3 hydroxide from grams. And now from moles of cobalt-3 hydroxide and into moles of the cobalt-3 nitrate. Then from moles of cobalt-3 nitrate, using that concentration term, we get into liters of the cobalt-3 nitrate. And then from liters and into milliliters. And now we look up the molar mass of the cobalt-3 hydroxide. So that's the sum of the cobalt's mass, 1 cobalt, 3 oxygens, and 3 hydrogens, for 109.9 grams per each mole. Then from the balance equation, we see 1 mole of cobalt-3 nitrate to 1 mole of cobalt-3 hydroxide. Don't just eliminate this step. If you take care of your units, they'll take care of you. So if you try to avoid this step because you know it's 1 to 1, you might find that your units let you down. Plus, it's not always going to be one-to-one, and you might find yourself developing bad habits. So fully use your units. Go through all these steps. And if you take care of your units, they'll take care of you. That's a promise. Okay, then the concentration term says 0.110 moles of cobalt-3 nitrate per liter of solution. 1 milliliter, 10 to the negative third liters. Or 82.7 milliliters. Does our answer make sense? Yes. Am I absolutely sure it's correct? No, I don't have that privilege, but I know at least it's reasonable, so I haven't made any gross error. Again, if I put that 10 to the negative 3 with the milliliters instead of the liters, a simple mistake, I would have 0.0827 milliliters, and that small volume would not make sense. You're not going to catch those mistakes if you don't ask, does my answer make sense? And you should be doing this in all of your classes, not just this one. Get used to asking that question every time you answer a problem. Okay, now we're asked to calculate the mass of the precipitate form. Okay, so we have a net ionic equation coming up. 125 milliliters of 0.150 molar sodium chloride and 150 milliliters of 0.100 molar silver nitrate are mixed. Okay, we have a net ionic equation, so we need to balance that equation. And let's see, we know sodium is soluble with chloride. How about with nitrate? Yep, we know that. All group 1A metals are always soluble with everybody, and nitrate is always soluble with everybody. So we just need to check the silver and the chloride, and oh, they do form an insoluble precipitate. So that's the precipitate that we're after. And it's balanced, so it's a 1-to-1-to-1 reaction. And any other preliminary steps besides balancing the net ionic equation? Yes, let's extend those bars under those molarities. I think we're good for all of our preliminary steps. So on to step 1. We're after the mass. So moles of silver chloride. Why don't I go to grams? We surely could. I'm just going to go to moles, and then whichever is a smaller number, that'll be the max. But you surely could go straight to grams, and a lot of students like doing it that way. Okay, but we're after a single unit, so we're going to start with that 125 milliliters of the sodium chloride. And from milliliters of sodium chloride and into, how am I going to get the moles of silver chloride? From moles of sodium chloride. We're going to get there from liters. Once we go from liters to moles of sodium chloride, we have just one more step to get to moles of silver chloride. And you could actually do one more conversion from moles to grams if that's the way you wish to set this up. Okay, 1 milliliter, 10 to the negative third liters, and that's 0.150 moles of sodium chloride per liter. And it's a 1-to-1 reaction. Just because it's 1-to-1 doesn't mean you don't need to do that step. Or 0.0188 moles of silver chloride, which seems to make sense. Same thing with the silver information, still after moles of silver chloride. We're going to start with that volume of silver nitrate, and then from milliliters of silver nitrate to liters, just like above, so we can go from liters to moles, and then from moles of silver nitrate to moles of silver chloride. 1 milliliter, still 10 to the negative third liter, and this time that's 0.100 moles of silver nitrate per liter of solution, and a 1-to-1 ratio of moles, or 0.0150 moles of silver chloride from the silver, 0.0188 moles from the sodium chloride. The smallest amount is the max amount. And so if you had already gone to grams, you'd be done, but Obviously I didn't. So I'm going to have to take that moles that we just calculated, and using the molar mass of silver chloride, go 2 grams. And the sum of silver's molar mass and chlorine's molar mass is 143.4 grams per each mole. And I come up with 2.15 grams of the silver chloride. Again, I'm going to ask, does my answer make sense? And it seems reasonable. Sometimes that's all you can tell, that it seems reasonable. But that's pretty much what you're looking for, that it seems reasonable. Because sometimes it definitely does not seem reasonable. An athlete running 13,000 miles an hour, does that seem reasonable? No. A molar mass less than 1? No. There's some things that just the size doesn't make sense. And by the way, a concentration more than 20 in molarity also would not be reasonable. 20 molarity is about the highest you ever get in concentration. Okay, balanced volume neutralization reaction, and we have selenic acid reacting with potassium hydroxide to form potassium selenate and water. Okay, my acid selenic acid has 2 protons. The base, potassium hydroxide, has a single hydroxide. These come multiple of 2 and 1 is 2. So I need 2 protons, so 1 selenic acid. 2 hydroxide, so 2 potassium hydroxide. There's always just 1 salt form, and it has 2 potassiums in it, and 1 selenate in it. And again, 2 hydrogen ions got together with 2 hydroxide ions to form 2 waters. Okay, we have arsenic acid reacting with calcium hydroxide to form calcium arsenate and water. Arsenic acid has 3 hydrogen ions. Calcium hydroxide has 2 hydroxide ions. These come multiple of 3, and 2 is 6. So I'm going to need 6 of each. For 6 hydrogen ions, I need 2 arsenic acids. For 6 hydroxide ions, I need 3 calcium hydroxides. I'm forming 1 salt, which has 3 calciums in it, and 2 arsenates. Again, I'm looking at the left to tell me how many calciums and how many arsenates. And 6 hydrogen ions got together with 6 hydroxide ions to form 6 waters. Okay, sulfuric acid is reacting with tin-4 hydroxide to form tin-4 sulfate and water. Sulfuric acid has 2 hydrogen ions. Tin-4 hydroxide has 4 hydroxides. The least common multiple is 4, so 4 hydrogen ions. So 2 sulfuric acid. 4 hydroxide ions, so 1 tin-4 hydroxide, forming 1 salt, which has 1 tin, and 2 sulfates. And how many waters were formed? 4. Okay, what is the concentration of an oxalic acid solution if 50 milliliters are neutralized by 44.2 milliliters of a 0.0751 molar sodium hydroxide solution? Okay, I'm using my units for this in the preliminary steps. I need to balance my equation. I need to pull out that concentration term. So here's the unbalanced equations. Oxalic acid reacting with sodium hydroxide. It's going to form sodium oxalate, and water. And I see a 1 to 2 to 2 to 1 ratio. I hope that you're able to do this on your own. And like I said, we also have that conversion factor to pull out. And now I think we've done all of our preliminary steps. On to step 1, we're after the concentration, so moles of oxalic acid per liter of oxalic acid. Then step 2, we're starting with one unit over another. Now we have 2 numbers with single units, the volume of the oxalic acid and the volume of the sodium hydroxide. which is going to go on the top and take us to moles of oxalic acid. The volume of the sodium hydroxide, the volume of the oxalic acid goes in the bottom and will take us to liters of oxalic acid. The milliliters of sodium hydroxide is going to take us to moles of sodium hydroxide by taking us first into liters. Then using that concentration term, from liters of sodium hydroxide to moles of sodium hydroxide. And again, the only way we can relate one chemical to another is through moles. So I hope we saw why we went into milliliters of sodium hydroxide first, because it was going to get us into moles of sodium hydroxide, and then we got to moles of oxalic acid from moles of sodium hydroxide. One more step, out of milliliters and into liters. I do recommend that you scratch out those units that cancel just to make it jump out at you that we have moles of oxalic acid per liter. That just helps it make it less likely that we'll make a mistake, or if we did, that we catch that mistake. Okay, 1 milliliter, 10 to the negative third liters, 0.0751 moles of sodium hydroxide per liter of solution. It's a 1 to 2 mole ratio, and 1 milliliter, 10 to the negative third liter. And since we have that 10 to the negative 3 on the top and on the bottom, we can scratch that as well. I come up with 0.0332 moles per liter. And that seems to make sense. When I look at the numbers, yeah, it definitely does make sense. Okay, that concludes our 4.2 to 4.3 lecture, where we began with solution stoichiometry. Again, stoichiometry, the relationship of one chemical to another, and the only way we can do that is through moles, and every time we have a new way to get to moles, we're going to revisit stoichiometry. We started with acid-base reactions to get us used to acids and bases reacting, and we saw how to balance neutralization reactions between an acid and a metal hydroxide, our most common of all bases. And then we just briefly talked about the strengths of acids and bases and how, when it came to the nanionic equation for each, they looked a little bit different. Then we jumped into acid-base stoichiometry, the real reason we're talking about acids and bases now. And then we also talked about that analytic technique known as titrations. Finishing off with our normal review.